Swayam Prabha. Digital India. Educated India.
I'll come straight away. Now, luckily for you and luckily for me, I thought of an example last night how to communicate this idea. Okay. Now imagine, number you are in Chennai, all of you are in Chennai. Okay. So this is Chennai. Written here, Chennai. You can see that is Chennai. The height of Chennai from mean sea level is 6 to 7 meters. About 6 to 7 meters. That's all. 18 feet to 20 feet. If there is a lot of ice melting, Chennai will go away. Okay. So from that Chennai, imagine I am going to roll myself to Namakkal. Somehow there is some mechanism, somebody is going to push me from behind, make me flat on the ground, and do this push. Okay. And if you push me to Namakkal, the average height of Namakkal means from the mean sea level is approximately 380 meters. Okay. So what will be the change in potential energy when you or me, we are rolled from Chennai all the way to Namakkal by some method, some roller is going to push you, take you all the way to Namakkal. Along some road, what will be the change in potential energy? It will be mass of you multiplied by the gravitational force which works down, multiplied by the height difference. Okay, this potential energy is a state function. State function means a function which will not depend on the path taken. If you are taken through, I can conceive of, as far as I know, easily 4 paths. There are multiple ways of going to Namakkal. Okay, you can go north and go. On the other hand, from here you can go directly south and west. South and west you have to go general direction. Okay. So, if you go along, there is one way, Pundamalli, Velur, Salem, Namakkal. There is one way. Okay. The energy involved and the work involved, the heat involved and work involved will be different for this path. If you go through Chengalpat being the common place, after Chengalpat, as soon as you hit Dindivanam, make through Thiruvannamalai, Arur, Harur or Harur as they say, and go up through Yelagiri hills to Namakkal. That is another second path. Third path is, at Dindivanam don't make a right turn, go further down to Ulundurpete, make a right turn, through Chinna Salem, Vazhapadi, Salem, Namakkal. There is a third route. There is a fourth route. Near Chinna Salem, there is a vertical going south called Nakka Salem. Through Nakka Salem, you can go to Namakkal. That is a fourth route. Fifth route. From Ulundurpet, go to Perambalur, Thurayur, Irumapatti, and Namakkal. And like that, you can write number of routes to go to Namakkal. Distance is always going from Chennai, some latitude, longitude to Namakkal, which is way above sea level. The work involved in this you obviously know work involved, bus fare, obviously everything, train fare, petrol, everything will depend on the path. So anything that depends on the path is a path function. Volume of petrol, cost of petrol, work involved, the amount of heat that goes out of your body as you do this work, they are all path functions. Whereas potential energy, which is not something that you can perceive, you cannot buy, is a state function. So, what is the convenience of using a state function and a path function is that it just helps you by relating the measurables, right? What is a measurable? Heat and work. For example, first law. Heat evolved or heat absorbed can be measured by measuring the change in temperature. What is the initial temperature? What is the final temperature? What is the mass of the object? You can measure system. Heat capacity you can measure experimentally. You must have studied this in +2. So, heat is a measurable function. Work done is a measurable function. You see that there is some change that can be measured, especially when there is a boundary that moves. It happens only in the case of gases. In the case of solids or liquids, you can ignore. There is not much of a volume change of a solid or liquid, but in the case of gas, boundary moves a lot. As in an internal combustion engine, when you inject a spray of petrol, boom, it just, because of volume exchange, the cylinder moves like this, and that is the work done and every time the cylinder is compressed back by the movement of the wheel, and this keeps on happening again and again. So, state and path function, is that clear? Okay. State function exists on paper, but you can correlate it with measurables through some equation, whereas path functions can be directly measured. Temperature on my, what is the temperature, what is the heat absorbed, what is the work done, all those things can be measured. Okay. So, that is the difference between state function and a path function. In mathematics, there is a definition I am going to tell you shortly. Okay. Mathematics gives a very simple definition of what is a state function. If it satisfies a certain condition, it is a state function. If it does not satisfy that condition, it is called a path function. That is for mathematics. But for layman, our purpose, this should be quite good. Remember this difference, and that is good enough. Is that clear? Okay. Now, can we start today? Okay. So, exothermic crystallinity morphology. Morph means appearance. Morphology means appearance. Okay. So, appearance for a matter would be more in terms of crystalline or not crystalline. There are two main categories. Is it crystalline? It is not crystalline. And if it is crystalline, there is single crystalline, polycrystalline. Okay, those are the definition within crystalline. Exothermicity has something to do with loss of heat. Energy in the form of heat is exothermicity. Does not connected with any of the this. Okay. Feel free to ask question. Then only sometimes it just helps me to gauge you. It helps you to gauge me, and then we can progress slowly. Any other question? From first two lectures are just giving you a feel for the subject. Nothing. We have not even touched the subject. Now only we are touching the subject. Okay. So first law, which we saw in the last class also, that for infinitesimal changes, du, the change in internal energy, infinitesimal change in internal energy is given by del Q minus del W, where this is the heat change, infinitesimal heat change, and this is infinitesimal work change. Okay. So, whenever it is a state function, the D will be full. Okay. When it is a path function, this will be used. Other than exam, this is of no relevance. Whatever I am teaching you, right, I am trying to share a concept with you. Other than exam point of view, when it comes to today's research, most likely not much relevant, a little bit relevant. Because philosophy is, any subject or anything in the world will have a basic grounding philosophy. Without a grounding philosophy, existence has no meaning. Okay, so any subject for us we call dharma, we call it as Vazhu Murai, we call it as this is how we live. We define our way by saying that this is my Vazhu Murai. Okay, within this is to make sure that good always prevails and bad does not prevail. This is a fundamental thing, okay, of life. Like that, the fundamental thing is that you have to know the basic thermodynamics. There are two advantages. One is exam, other is whenever you study any difficult problem in research, the tricks you learn here will set your path in the brain in a different way. So, you are able to address your problems, not even knowing what was the real contribution why you are able to address a problem. Tomorrow, you might be able to make a particular molecule by a certain pathway. Okay, you think that this came to your brain by an instinct. No, the back of your mind is all these paths which are working. Whatever you learn in a course, it teaches you multiple ways of thinking. Okay, and that is only a second major advantage, and that is the intended advantage of any teaching. Any university, any school, any college, that is intended is to teach a skill. The skill will help you when you actually meet a real problem. Okay, this first law will not help you meet a real problem. The skill that you learn in first law will help you to understand a real problem. So, for finite changes, we always write this delta. Okay, that means that is something measurable, not infinitesimal. Measurable, you use this delta. So, this is the heat and work factor, and most important thing we saw in the last class about W, that if the work is done reversibly, the work done is reversibly, then the total work is given by integral PdV. Okay. And for a perfect gas under isothermal conditions, we said that the work done is given as Nr. P is, it should not be T, I think you made a mistake here. Okay. P equal to RT. Okay. It should be energy unit. Okay, no problem. So nRT ln V2 by V1. This should have the unit of energy. RT is the unit of energy in joules. So answer is correct. So if it is an irreversible process, it is given as P external multiplied by delta V, where delta V is the change in the volume. So first an important thing, we stopped here in the last class and we will go to the next one. Okay. So at constant pressure, let us say it is an isobaric path that you are following, then the first law can be written as du equal to Q has a subscript P. The subscript P says that there is a constant pressure path. Okay, QP minus PdV, right. So this QP then will become, if you take the PdV and put it on the other side, that will become du plus PdV equal to QP. That is a heat absorbed under constant pressure, when the constant pressure path is defined, is given by the change in internal energy plus the work factor. Same first law rearranged, that is all, right. Now, since it is an isobaric process, P is a constant, I can simply add a term VdP, because dP is anyway 0, there is no change in pressure. I can add VdP, I can add TdP, I can add many things, as dP is going to make sure it becomes dead. Okay. So I add VdP, then you find that QP is du plus PdV plus VdP, then you see that this is a perfect differential du plus PV. Okay. So heat absorbed under constant pressure is given this term U plus PV equal to H, which is nothing but enthalpy. So enthalpy is the heat absorbed under constant pressure. So whenever you want to measure a enthalpy change, you will always see how much of heat is given out or absorbed under constant pressure, which is 1 atmosphere. Now if reaction takes place under this condition, 1 atmosphere, the heat absorbed and given out is enthalpy. So that is a definition that first law comes up with a new factor known as enthalpy, which can be measured from a calorimetric experiment. So you will take a bottle, water bottle like that, to that water bottle, what we will do is take sodium hydroxide 1 molar, add 1 molar 10 ml, 1 molar of HCl, again 10 ml, mix the two, lot of heat will come out, you put a thermometer, measure the heat change, then you will find the enthalpy change or heat of neutralization, we call it as the heat of neutralization. So absolute value of H cannot be determined, but change can be determined. So any absolute value of U or H cannot be measured, but changes in internal energy and enthalpy are measurable. How will you measure the change in internal energy? If you do the same experiment under constant volume. So what constant volume means what? This term, what happens to this term, PdV term, work term, disappears. So here I use a V. See, I am going to use a V, okay, constant V. I put a constant V and this term will become 0 because dV is 0. So du is nothing but heat absorbed or given out by the system at constant volume. So delta U, which is a state function, can be measured by the amount of heat absorbed or given out when the volume is constant. You ensure that volume is constant, do a calorimetry experiment, you will find delta U. Do the same experiment, make sure pressure is 1 atmosphere, then you will find the enthalpy. So enthalpy is N, number of moles, Cp, heat capacity at constant pressure, multiplied by the difference in temperature that arises when two things mix, or when two things react, or when something evaporates. Very simple. What is enthalpy of sublimation? Same thing, Ncp delta T. Upon sublimation, what is the change in temperature? Multiplied by heat capacity, multiplied by number of moles. So it is very easy to measure changes Okay, this is the example I wanted to, you asked at the beginning of the class, I had prepared for this last night. Okay, so this is Namakkal, northeast, and Chennai, this is the northeast. So roughly 218 meters. So I have somewhere I had written this wrongly, 218 meters. 218, Namakkal is 218 meters above, and you know that the potential energy change is nothing but the change in the height multiplied by mass into gravity. That is a state function. But work function and heat function can easily be measured by, as we do the work. Okay, we can measure using a appropriate method like thermometer or something. So you can measure all. So what is a state function? Mathematics defines a state function as a function phi, okay, is a state function. D phi, which is a function of x and y, is a state function if dou m by dou y at constant x equal to dou n by dou x at constant y. So phi is a state function if you take the derivative of m with respect to y dy and take the derivative of n with respect to dx, then it is an exact, if these two terms are equal, then it is an exact differential. The mathematical way of saying this. Okay, apparently potential energy, somebody must have done proof for this, that potential energy is a state function by doing this. Potential energy is a position of, by virtue of position. So somebody must have done this xy, right? So we know this already. The internal energy change is a heat absorbed or given out constant volume. Now these two, that heat factor, that is du is NCV dt and dH equal to NCP dt, we just went through, right? Any question on this? So this is something that just we saw few minutes back. Okay, I am just repeating this again and again. Okay, now from the first law we already saw that there is a new state function known as H, which is given as u plus PV, and again by simple differentiation you can find out that dH equal to du plus PdV plus VdP. Put constant pressure, this term vanishes. So dH equal to du plus PdV, and at constant pressure it is nothing but the heat absorbed and given out is given as dH. Okay, so these are two important terms that you need to know. These two important terms are internal energy change can be measured in any system by carrying out a transformation under constant volume, okay, provided you know the number of moles present, heat capacity at constant volume, multiply by the change in temperature. So this will tell you what is internal energy change, and this will tell you what is the enthalpy change. Okay, these are state functions as opposed to heat, which is a path function. How did heat become state function here? Because you put a constant path. You define the path by saying that heat absorbed at 1 atmosphere pressure. You define the path, then Q becomes Qp delta H. Again Q at constant volume, you put the constant volume condition, define the path, isochoric path, then Qv became delta U. Then it became a state function. So state functions are path, they are not path specific. Okay, that is the big difference. Now this is first lecture. I was supposed to have finished it in the last class itself. So that has already taken nearly 20 minutes to extra. So what is the purpose of the second law? We are now going to see. First law was already known, law of conservation of energy. I told you karanam karyam. First karanam is that you cannot produce energy in the universe. It is there, one constant thing, everything undergoes transformation. Now that in chemistry was not adequate, and also not adequate in the real world also. So we are going to look at this issue from the chemistry point of view. From the chemistry point of view, we often ask, there is a periodic table of elements, there are billions of molecules. Okay, if I want to know a given transformation will take place or not, is there any simple way of writing and finding out whether it will take place? Okay, so let us take an example. Okay, this is really where thermodynamics will help you when it comes to research. So you know that today hydrogen is in big demand. Okay, although the nature given fuel, hydrocarbons are there, they cause pollution, number one, and they are available only to few people in the world. Okay, Middle East people, for some reason, they seem to have lot of oil. In the US there is a lot of oil. In Russia there is a lot of oil. In South America few states have oil. But two major countries, two really big countries which need energy don't have oil. One is China, other is India. We use lot of oil, but we don't have oil. So every 100 rupees earned by the Indian country, nearly 60 rupees is spent on purchase of oil and gas. 25 rupees for purchasing gold. If you want to know what our country is, if somebody asks you, 60 rupees is spent on kerosene, 25 rupees on this. What is the balance available for spending? 15 rupees. With that 15 rupees, Government of India buys industrial equipment, okay, TV, fridge, washing machine, etc., etc. Everything that you need is purchased with that 15 rupees. How will you run a family if you use 60 rupees for buying fuel? You should keep the fuel to about 20 rupees, right, or less, so that you have enough money to buy other things. But we don't. China doesn't have. China addresses the problem in a very beautiful way. Now they have what is known as fusion research. Okay, this is very modern. Suppose you go to any nuclear energy research center for PhD or for work, you will find that today nuclear fusion is the way to go forward. Thorium is fused using what is known as metal salt, molten metal salt as a coolant. It's a very safe way of doing fusion reaction. Thorium is present in really large quantity in a substance known as monazite sand, which in Tamil Nadu is available in Thuthukudi. Okay, Thuthukudi, somebody here said from Thuthukudi, no? Somebody here said monazite sand. Vaigundarajan, who is very famous for the guy for selling sand, not by the lorry load, by the ship load. Vaigundarajan along with Sasikala, they formed a alliance and sold ship loads of monazite sand to all over the world and made lots and lots of money. Of course, that helps you build a house in Poise Garden, it helps you build a house in Thuthukudi or a hotel you can have, everything. But you don't realize the value of the monazite sand. Monazite sand has thorium. Thorium can be fused to generate energy by fusion. Green process, there is no danger. You can actually generate electricity. And if you can generate electricity, we don't have to depend on Arab countries. See, all our policies are very complicated, in a complicated way, dependent on we have to please the Arab countries. If they stop oil and gas, we are dead. Okay. Others who supply, Russia can also now play politics, America can play politics, but we need oil and gas desperately. Okay. So, and we don't have a alternate means of generating energy. Right now, yesterday I told you, 30% of our energy comes from solar energy and wind energy, but that is not enough. You should push it to 70%. Then you will have more money to spend on internal needs like education, good roads, healthcare, right? Instead of spending on petrol, you will spend it on people. So that is a big change that will come about. So the point is hydrogen. I started with hydrogen. Hydrogen is a fuel which is needed. Now, what is the natural abundance of hydrogen? So this is where your research problem starts. How thermodynamics can help you with the research problem. Tomorrow when you address a research problem, hydrogen, what is the natural abundance of hydrogen? How much of hydrogen is abundant in nature? As it is hydrogen H2 molecule, what is the natural abundance of hydrogen? Not in compounds. Should not take it as CH4, C2H6, kerosene. No. What is the natural abundance of hydrogen? First question. You ask yourself. Go to room and check. Google it. Google is a good teacher. Second thing is, what are the means by which you will generate hydrogen? How will you generate hydrogen? What are the means? Electrolysis is one mean. Is there any other means of generating hydrogen from compounds that exist in nature? Already there. All I need to do is simply put it in a bottle, supply light and you should get hydrogen. Is there any means? Is there any way of doing it? You have to check. I don't know. Okay. Is there any way of trapping hydrogen, holding hydrogen so that when you want, hydrogen can be released? So research problems come like this. Okay, hydrogen is required. How will I make hydrogen? Can I make hydrogen by taking ethane gas, which is available, and in a mild manner I develop a catalyst and get ethylene plus hydrogen gas. Is this reaction as I propose to you spontaneous or not? This is a question that chemistry people will ask. Suppose I take ethane, can I use some catalyst, don't spend too much energy, and get ethylene and hydrogen? Is it possible? What you need to do is, today hydrogen is the demand. What are the ways? Write 10 different ways of generating hydrogen. You will find that all 10 are not sustainable. Write 100, maybe one will be sustainable. Write 1000 reactions, out of 1000, maybe 10 will succeed. In that 10, something has to work out practically to make hydrogen gas. That is a challenge. The challenge to us is, how will you? So for that, what we need to do is, what is the direction of natural transformation? Is it to know what is the direction of the natural transformation? How will I know it? By inspection. I want to just look at it and then say, this will take place. No, this will not take place. So second law purpose is both from the chemistry point of view, direction of natural changes. So what I am going to do is, how the second law and third law that are going to follow, you are going to see that entropy is a fundamental factor. Entropy changes which tell us something about the direction of natural process, and how absolute entropy can be measured using a third law. And next 2 lectures we will talk about free energy and free energy changes. And with that, what are the terminologies I will use? S is a terminology for entropy, you already know this. ds is always infinitesimal. Why have I used capital D? Because entropy is a path function, we are going to show shortly. Okay, and delta S means finite change in entropy, and this is a definition. The definition is that entropy change, infinitesimal change, is given by infinitesimal heat absorbed divided by temperature. Okay, what is entropy? Entropy is defined in this manner. Now, these are the terminology I am going to use. Now, this is somewhat already 9:30, we have only 20 minutes. So, what I am going to do is somewhat go a little faster. Okay, is it okay? Because you don't have to read through every slide. If you want, I will give you PDF form, slide in PDF form. So, question is, in chemistry, it was always thought that exothermic reactions are spontaneous. Why exothermic reaction is spontaneous? I jump like this, my knee is not that strong. I am old, so I am not able to bear the shock. Okay, that is spontaneous, no? If I jump, what happened to my energy? Potential energy came down in the form of heat. I didn't measure. So very simply, this logic was used to say that all exothermic reactions are spontaneous. The chemistry terminology before second law was, all exothermic reactions are spontaneous. Anything that comes downhill is spontaneous. Okay, so here are 2 examples. Hydrogen gas plus oxygen gas is a beautiful example from the point of view of demonstration. Suppose you take hydrogen gas in a bottle, oxygen gas in a bottle, bring them together, nothing will happen. On the other hand, when you bring them together, you bring a platinum wire, okay, nothing will happen. Take the platinum wire and place it on a Bunsen burner, clean up the surface, burn out all organic contaminant on the platinum surface, and then bring these 2 together with a platinum wire. You will not be there, you will be dead. The reaction is so fast. With clean platinum wire, hydrogen and oxygen explosively reacts by a reaction known as branching chain reaction. Not even a chain reaction, branching chain reaction, which is very similar to nuclear fission reaction. So this reaction, this H2 plus of O2, is a slow reaction under certain condition. With platinum, clean platinum, exceptionally fast reaction. But it is a spontaneous reaction. I am going to use this again and again and again. Reuse. Spontaneous means it will happen without external intervention. In this case, catalyst is there. But even without catalyst, it will happen. Slowly it will happen. Spontaneous means nothing to do with speed. Spontaneous has something to do with it will happen. It will happen. Don't worry, Machan, it will happen. That's all. It will happen. When it will happen, it will happen. It will not happen. No matter even if you stand upside down, that is non-spontaneous. That is spontaneous and non-spontaneous. So, this reaction takes place spontaneously. Rusting of iron, one of you gave the example, is a spontaneous reaction. It will happen slowly, fast, conditions will vary. So, this is an exothermic reaction, this is also an exothermic reaction. So, can heat given out or absorbed stand as a criteria for spontaneity? That is, if heat is given out, spontaneous. If heat is absorbed, then the way reaction return is non-spontaneous. So, we ask the question from the first law point of view. We have two state functions, delta U and delta H. So, with this, can we predict from the sign of delta U and delta H, is it possible to predict the direction of natural reactions? Okay. Here are exothermic reactions, few more examples. Here is sodium plus water, doesn't require any catalyst. Don't even try that. Tiny bit of sodium on water, on your face it will explode, because electron transfer reaction on the surface of sodium is extremely fast. Sodium, electron on the surface of sodium is dying to find some partner. Okay, it is really at the edge of life. I want to die, I want to ionize. Okay, sodium wants to become sodium plus, electron will be transferred, instantly there will be a kill and there will be explosive reaction, sodium plus water. So, spontaneity in the thermodynamic sense indicates direction of change and not rate of change. I will keep on repeating this till I retire, because oftentimes spontaneous, students always think of this as something to do with rate. No, spontaneity has something to do with the direction. At the end of this course, you will go back to your colleges. That is a spontaneous thing that will take place. Okay, not it's spontaneous doesn't mean instantly. Spontaneous means what is the natural direction. Okay, so, but
This process similarity to electrochemistry in fuel cell process, and because of H2 to water molecule.
we are going to see this, that this is known as a fuel cell. In a fuel cell, fuel is hydrogen and air. Hydrogen and air, platinum is the catalyst, and you have a anode and a cathode and membrane that separates it. Hydrogen reacts on one side, oxygen reacts on another side to form water and generates about roughly 1.23 volts, and that is the fuel cell that I told you about railway yesterday. That railway, Indian Railway wants to run the engine, internal combustion engine, with this supply of electricity from a fuel cell. Okay. Now, this reaction, these are two interesting, I am going to show you a third reaction also. This reaction, barium hydroxide, you can do this if you have access to barium hydroxide in your lab. Okay. Barium hydroxide, ammonium chloride is readily available. You mix the two, this will spontaneously cool down without any external intervention. No external intervention, it will become cool, extremely cool. Okay. So, it is happening spontaneously. What does that mean? Heat absorbed is now become the condition for spontaneity. Previously, I jumped and showed you heat liberated should be the condition for spontaneity. So, first law, there is something wrong, heat absorbed. And here is another reaction, sodium bicarbonate plus acetic acid forming this salt. Again, this is a endothermic reaction. Now, common thing that I can illustrate this with is, you go to pharmacy and ask for a cold pack. If you ask a pharmacy for a cold pack, why should you ask pharmacy for a cold pack? Invariably, if you are a sports person, you will be subject to some injuries. Okay, suddenly one day it happened to me, I couldn't do anything about it. Okay, I was playing badminton, shuttle badminton, and I slipped. Okay, and my right foot bottom part, I could not address the problem immediately. Normally, what you should do is go to a pharmacy, ask for a cold pack, and the cold pack consists of two packets. One is ammonium nitrate solid, other is just plain water. Ammonium nitrate and plain water, when you mix, it becomes very cool. So you have to apply the cold pack on the injury spot before you go to a doctor. Doctor is only second step. First aid is apply cold pack. So that is an endothermic reaction. How is endothermic reaction happening spontaneously? It is happening without any external intervention. So the criteria that exothermic reactions are spontaneous, endothermic reactions are spontaneous, or both are wrong. Okay. So this is the limitation of the first law when it comes to chemistry point of view. We want to find out whether some reaction will take place, heat absorbed, or whether it is exothermic reaction or endothermic, both seem to be spontaneous. So that is the limitation. So we need to go for a second approach, and here many more things, examples I have given here. Okay. Iron and steel, when exposed to air and moisture, rust spontaneously. If the temperature of water goes below 0 degree, as in the upper atmosphere during winter, ice or snow is formed spontaneously. Yesterday also we saw an example, when the window or glass is cooled, water will condense. It happens spontaneously. Okay. Spontaneously means without any external intervention. In this case, glass is being cooled. In the case of atmosphere gets cooled when there is no sun. When there is no sun, why did water condenses? So exothermic reactions or endothermic reactions, as a criteria for spontaneity doesn't work. Okay. And the most important point that was observed experimentally is that exothermic reactions, all exothermic reactions, when you increase the temperature, you reach a ceiling temperature known as ceiling temperature. At the ceiling temperature, spontaneously it goes in the reverse direction. Okay. And endothermic reactions, like the example of cold pack I told you, if you go down in temperature, it goes in the reverse direction. So why is temperature deciding the direction of reaction? And that seems to vary from one reaction to another reaction. For some reaction, temperature goes up, reaction goes in the reverse way. For some reaction, temperature goes down, reaction goes the other way. So these are practical things I am telling you that you see in a lab. Okay, exothermic reaction, spontaneous. Sometimes exothermic reaction, not spontaneous when you increase the temperature. Endothermic reaction, spontaneous without anything. Endothermic reaction, non-spontaneous when you cool it. What is this? So there must be some uniform criteria. You should be saying that this changes, this will be spontaneous. If this doesn't change, then it will be non-spontaneous. So is there any one single criteria that we can use? Heat is not a criteria. Heat evolved or heat absorbed is not a criteria. Okay. So that is what we see. Then what you can see from this, that first law is not adequate. So that is a need there is a need to go for the second law of thermodynamics. Now you remember the state function. Okay. A state function, wait a minute. This is a state function, right? Phi is a state function if this condition is satisfied. So from the first law, let us see, can you generate another state function by using the first law itself. Okay. So what we are going to do is divide the heat absorbed by a temperature. Heat absorbed or given out by temperature, Q by T. Instead of trying Q is a path function, we know that. Is Q by T a state function? Ask a question. Just divide Q by T. Ask a question. Succeed, fine. Not succeed, no problem, right? So that's what we are going to do now. So Q is not a state function, proof is straightforward because this is the first law, dQ equal to du plus P dV. Du is nothing but, now see it is useful, for 1 mole Cv dt, n moles n Cv dt. Okay, now you see where this is useful. So d phi equal to m dx plus n dy. Take the dou m by dou v, dou n, dou p by dou t. Find that these two terms are not equal. So one is 0, other is r by v. Therefore Q is not a state function. Heat absorbed is not a function. Now let's do this. Same exercise, but now divide dq by t. So whatever we did previous slide, divide dq by t. When you divide dq by t, it will become cv by t dt, so this term, and p by t dv. So the expression we are looking for is, this is d phi now, m dx n dy. D phi equal to m dx plus n dy. Phi is a complete differential if dou m by dou y at constant x equal to dou n by dou x at constant y. So dou m, this is m, so dou m, so this we are going to do a derivative of this. So dou of Cv by T versus dV at constant T. Cv is heat capacity at constant volume. It will not change. If volume is constant, it will not change. So dou Cv at constant volume will be 0. So this will be 0. Now do the same thing for the right hand function. P by T is R by V. So dou N by dou T at constant V. Now this is at constant V. This is at constant V. This is at constant V. That means R by V is a constant. V is constant. R by V is constant. Now therefore this constant by dou T is of 0. When you differentiate a constant with respect to a variable, it is 0. So left hand side is 0, right hand side is 0. Therefore dq by T is a state function. Okay, and you can try many functions, and that's what was done. So it was observed that when you divide the heat absorbed or given out by the temperature at which it takes place, then you get a new state function. So we get a new state function. What is the relevance? We are going to see, but before we see, we will do some small exam type problem. So what is the significance of this term dq by T? So consider an isothermal. You saw this in yesterday's blackboard. Y-axis is pressure, x-axis is volume, and there is infinitesimal change in volume at constant pressure. Okay, or dynamic change in pressure means there will be very tiny change in the area under the curve. Okay, tiny change in pressure, tiny change in volume. Tiny is really tiny, that tiny. Okay, so what this new factor q by T is nothing but for every one of this tiny step, the change in heat divided by temperature is known as the infinitesimal change in entropy. Okay, so every dq by T is the entropy. Say dq, and this is a reversible path, so we call dq reversible by T as ds, that is defined as entropy. So what is the finite change in entropy? Finite change in entropy delta S is given as S2 minus S1 from path 1 to path, from system variable 1, state 1 to state 2, dq reversible by T. This part is clear. dq reversible by T is ds. So integral of ds will be delta S. That is the entropy change. Okay. So take the example of an isothermal reversible transformation. Isothermal reversible transformation, which is very fundamental from exam point of view. Okay. Isothermal reversible reversible, let's take an expansion. So delta S is equal to S2 minus S1 integral P dV 1 to 2, and let's say this is a perfect gas. So this is a perfect gas, P equal to RT by V if it is 1 mole, if N equal to 1. So delta S equal to integral RT dV by V. Okay, isothermal. So that means this is constant. So this will be RT ln. So entropy change for an isothermal reversible expansion of a perfect gas 1 mole is given by this expression. If it is N mole, Now, how is this a useful criteria? We are going to see shortly. Shortly we are going to see. Okay, you require to adopt a certain way of looking at the issue. So, this is for isothermal transition. S is a state function we just saw. Entropy is an extensive property and its unit is, since it is heat divided by temperature, heat is energy, joule per mole is heat, divided by temperature Kelvin. Joule per mole per Kelvin is a unit for entropy. Okay. So, very easy for you to remember that T delta S has the same unit as energy. T delta S has the same unit as heat, or it has the same unit as energy. And there is something, whenever any transformation takes place in the system, there is a corresponding heat absorbed or given out in the surrounding. System there is some transformation, but that will take place only when there is some proportional transformation in the surrounding. Okay. So, the surrounding change in entropy is defined by this term, just take it as a definition. Whatever is the heat absorbed or given out by the system, put a minus sign, divided by temperature at which it happens. For example, this class is going on, okay, and this class is generating lot of heat, and there are air conditioners. All the air conditioners do is 30 plus 1, 31, 32 people, there is one more person, 33 people are giving out lot of heat, on an average some joules. Okay, this heat 33% multiplied by, let us say, 100 joules, that is happening every minute. 33 people, 100 joules every minute, 3300 joules are being dumped outside, but outside temperature is much higher than this. So, change in entropy of the surrounding is 3300 joules, heat is being dumped out. So, change the sign, put a positive sign, minus sign becomes positive, divided by outside temperature is 32. So, 273 plus 32, that is a change in the entropy of the surrounding. What is the change in the system? Our temperature is maintained at 25 degrees, and how much of heat we have lost? Same, minus 3300. Our change is different from that happens outside, and this happens spontaneously because the universe allows it. The change here is minus less, change outside is plus more, plus plus minus gives always a plus to the outside, and whenever there is a increase in the entropy of the universe likes it. Okay, classes can go on, continue the lecture till 9:50, give a 10 minutes break for going out. So, that is allowed by the second law. Okay. So, this is entropy change in the surrounding is always defined as negative to the heat absorbed or given out by the system. System will either give out heat or absorb heat, put a minus sign, divide by the temperature of the surrounding, because it is accepting heat at a certain temperature. So, temperature of the surrounding, that is the heat, that is the delta S of the surrounding. Okay. And in an adiabatic transformation, what will happen? If it is an adiabatic transformation of a system, the Q is 0, no heat is given out. So, what happens to the entropy of the surrounding? 0. So, only when the system entropy increases, spontaneous transformations can take place in a adiabatic system. If the system is adiabatic, insulated by, no heat can go out in the system, then only when the entropy of the system increases, it will go. When the entropy of the system decreases, no, non-spontaneous. Okay, spontaneously it will happen if the entropy of the isolated system increases, and that is one form of the second law of thermodynamics. Okay, now let us go to classwork, and with this classwork I will stop and you can go for a break and come. Now, this will explain this very hopefully very clearly. Let us take 5 moles of an ideal gas. N is 5. Closed container, that means closed system, subjected to isothermal expansion at 32 degrees centigrade. In chemistry, whenever you are given anything in degree centigrade, go immediately quickly convert it to Kelvin. 273 plus 32 Kelvin, absolute temperature. In this process, its volume is doubled. So, initial volume is V1, final volume is 2V1. Find the magnitude of the delta S system, delta S surrounding and delta S total in the units of entropy for the following three processes. Okay. First is a reversible expansion, second is irreversible expansion where the energy absorbed is 1000 joule less than the reversible expansion, and third is free expansion. Free expansion always means external pressure is 0, that is it is expanding against the vacuum. Okay. So with these three conditions, find out this. When you work it out, you will really understand entropy very, very nicely. So first is an isothermal expansion, right? It is given. N is number of moles is 5. So what you will substitute here, N equal to 5. R is 8.314, depends on the unit. When you want in joules, always use joules. So 8.314 for joule unit, and V2 by V1 is 2, twice the volume change. So this will be 5 into 8.314 into ln 2, which is nothing but 28.8 joule. You can verify this. Okay. Since there is no mole here because it is for 5 moles. If it is per mole, you have to divide it by 5. Okay. So first question is reversible expansion. In reversible expansion, entropy change in the system and surrounding are exactly the same. Okay, we are going to see this shortly. Before that, I need to show you a problem, that's why I showed. Okay, so these are exactly the same. Nothing happens to the universe. Okay, delta S equal to 0 means nothing happens in the universe. The system is in equilibrium. System is in equilibrium means it's nothing is happening. Something is happening here on in equilibrium. Always something will be happening, but not anything that will affect the surrounding. Whatever happens within the system, so that there is no net change. No net change. Change will take place. No net change, and outside nothing will happen. So this is the case 1. Okay. Now next case is the irreversible expansion. That is when the heat absorbed is 1000 joule less than the reversible case. Okay. So what is given is delta S system. So S is a state function. It does not matter which path you go, as long as the initial variable and final variable are the same state functions, P, V, T, delta S will be the same. Delta S is a state function. So that's where, so independent of whether you do expansion by reversible or irreversible path, as long as, see, this is a problem in paper, in reality this will never happen. Remember, all we are only understanding concepts. Okay. In reality, by an irreversible expansion, you can never take a system from on P1, V1, T1 to the same P2, V2, T2. But assume that it is there. Okay. Just for paper, doing problem, we are doing this. Okay. So reversible expansion, as long as the final P, V, T is the same, delta S will be the same because it is a state function. But delta S surrounding is 1000 joule less, right? So let us find out what is delta S surrounding. Delta S surrounding is minus Q system by T. So Q reversible is delta S system into T because Q by T is delta S system. So this is 28.8 into 305, which is 8788.3 joules. That is, in the reversible case, 8788.3 joules of energy was dumped outside to the surrounding. In the reversible case, the expansion. In the irreversible case, you are given the problem saying that there is an irreversible case where the heat dumped is 1000 joule less. Problem itself states that. So you subtract 1000. In the irreversible case, 7788.3 joules is the heat actually dumped to the surrounding. If this is the heat dumped to the surrounding, the change in entropy of the surrounding is minus 7788.3 divided by 305, which is minus 25.5. You do the calculation. Delta S total is system independent of reversible path or irreversible path, as long as you take it from state 1 to state 2. See, remember, no exam, they will not give all this clarity. You have to always assume that whenever anything is given, you are going from one state to the same state. Nobody will say, write this all in black and white and red, going from state 1, P1, V1, T1 to P2, V2, T2. A, reversible path. B, irreversible path. They will not give you. You have to assume. Because this is a training purpose only. In reality, this never happens. So, this will be change in the system entropy, surrounding entropy 3.3 joules. So, for irreversible case, the delta S total is 3.3 joules. Last one very quickly, free expansion, P external is 0. If P external is 0, what happens to the delta S system is 28.8, same for the same transformation of state from 1 to 2, assuming that delta U is Q minus 0 into delta V, okay. So, pressure is 0, external pressure is 0. Internal energy of a perfect gas depends only on temperature, and if it is constant, then U is invariant. A perfect gas, its internal energy will depend only on temperature. PV equal to nRT, T depends only on temperature. So, if internal energy does not change, there is no work, heat change is 0. So, that is what is being written here. So, delta S surrounding is 0, delta S total is 28.8. This is a very important problem, and we can take a break now, but remember that you have to keep asking questions. Sir, how is it possible for you to take a system from P1, V1, T1, n number of moles to P2, V2, T2, n number of moles, both by the reversible path and the irreversible path? It never will happen. Reversible path will go to some P1, V1, T1, irreversible path will go to some other one. But exams will never define this to you. It is assumed that you know it is a textbook problem, it has nothing to do with real problem. So, assuming that it is going to the same state, we are doing all this, okay. So, here we take a small break.
SwayamPrabha, Digital India, Educated India.